So the first talk is on non-polynomial worst-case analysis of recursive programs, and Hongfei is going to give the talk. Please go ahead.
So in this talk, we consider the worst-case analysis of programs. So here, so you may have listened to my previous talk, which is about recurrence relations. Here we really target programs. So so our focus is tight committed bounds for programs, especially recursive programs, and we aim to develop automated approaches for this for this problem. And this is a very important problem because it has many applications. For example, we can apply this to analysis orders with non-trivial complexity, and we can also apply this to embedded systems where there are many time-critical applications. And we target recursive programs. The motivation is that recursion is a very important program paradigm, and it also is the major source for those non-trivial and non-polynomial worst-case behavior. So since it is a very important problem, so there are many previous results. So first comes the approach of ranking functions. So we can see that there are many variants of ranking functions. And then we also have recurrence relations. And there are many other approaches. So it's a very important question, and it's a very hot question. So in our result, we consider worst-case analysis with recursive programs, and we do it also through ranking functions. But our approach is somewhat different and new from previous ones. So first, we obtain a theoretical link between ranking functions and worst-case analysis. So for previous results, either ranking functions is not related to the worst-case behavior, or it needs some aid. It needs some extra aid, such as evaluation trees, to achieve tight worst-case analysis. And then we show an efficient approach for synthesizing non-polynomial ranking functions. And finally, our approach is an efficient one for synthesizing exponentiation bounds, such as n to 1.6. So we also target simplified, but it is also a rudimentary language. So in this language, we have basic structures for recursion, such as we have assignment statement, conditional branches, we have while loops, and we also have procedure calls. We do not consider return values at this stage because many recursive because the running time of many recursive orders they do not rely on return values. So let's give an example. It's a very simplified example, which is from binary search. Here we abstract away all the array operations. We just focus on from this simple program which captures enough information for deriving worst-case analysis of this program. So we first develop a notion of ranking functions for recursion, and then we synthesize non-polynomial ranking functions so that we can obtain a non-polynomial and tight worst-case analysis for such programs. So here is some key aspects in our approach. So we consider ranking functions over stacks. And I think this is a novelty, and then we focus on the ranking condition for procedure calls, which is the core to our notion. So let's take an example of this binary search program. So we first establish a notion of intermediate function, which assigns to each label and each value a non-negative real number, and then we somehow need to transform this intermediate function into a ranking function. And the transformation is defined through summation. So for example, if we have a stack which contains just 2 elements, which is FL25 and FL12, and the transformation just takes the summation of all the elements in the stack. So it's the value of h at FL25 plus the value of h at FL12. Of course, not every intermediate function can induce a legitimate ranking function. There are some constraints for such functions, so that they really induce ranking functions. So we need to have constraints for those functions, and they can be classified into non-negative constraints, zero value at the termination constraints, and also the most simple one is ranking condition. So first comes the two very simple conditions for ranking functions. The first one is called non-negativity, which means that the value taken by this intermediate function should be non-negative. And we also require that upon termination, the function should take value 0. And now we take a look at the most simple one, which is ranking condition. So our notion of ranking function are a sort of a technical extension of normal ranking functions without recursion. So we inherit many aspects from ranking functions and for non-recursive programs. So for example, for this assignment statement, we follow the standard for ranking functions. So it just says that the value of h at the successor label L prime under the assignment 2n plus 1 is smaller than at most the value of h at the label L minus 1. So here 1 is the positive amount to decrease. So similarly, we also inherit conditions for branches. So here we see that the ranking condition says that the value of h should decrease by at least 1, conditioned by the logical formula of this conditional branch. And we also have this the condition for non-determinism, which is also standard. It says that the ranking condition should hold at every branch of this non-deterministic choice. And finally, we come at the very important condition for recursion and the procedure cost. So here we see that within the function property of f, we call a function we call a procedure G with the value passing function 2n plus 1. And the ranking condition says that the value of f at L prime, which is the successor of L in f, plus the value of h at G. Sorry, there is some typo. So here this L should be the initial label or the initial program counter of G, and under the value passing function 2n plus 1, and this value should decrease at least by 1 compared with the value of h in the function property f and at the label or program counter L. And this is an example. So we have that at the terminal program counter the value is 0, and L3 is obtained from L4, and then we also have the non-negativity conditions for L1 and L2, and the last three conditions is from ranking conditions, and the last one is from the recursion at L2, which causes the function f itself. Yeah. And we have the soundness commits, which ensures that first, if we have such an intermediate function h, then this serves as an upper bound for the worst case behavior. And we also have the completeness, which says that the worst case behavior function itself is a legitimate intermediate function. Now we came to the synthesis of non-polynomial ranking functions. So we first established a template with unknown coefficients and also with non-polynomial terms. And then we establish constraints for those unknown coefficients, and these constraints are essentially ranking conditions. And then we solve the coefficients from those constraints through special methods. So first, we establish a template for, say, this Binarysis example. So the most important one is the function at L1, where we have this C1n plus C2 log n plus C3. Here, C1, C2, C3 are the unknown coefficients. And then we obtain constraints from those ranking conditions. So here we skip the details. We just see that they are universally quantified logical formulas, whereas the last one is obtained from the ranking condition for recursion. So here we see that there are some non-linear terms, so there is some difficulty. The difficulty is that the theory of non-polynomial arithmetic is undecidable. So we solve this problem by abstraction of those terms. So let's take an example. So in this example, we see that log n and log the flow of n over 2, and also there are some non-polynomial terms, and we just abstract them with the fresh variables, and we obtain those new formulas. But we need to keep consistent of the relationships between n and the new fresh variables, and then we perform. And then we add new constraints for those variables, namely from flow expressions, logarithm, and also Lagrange's mean value theorem. And then we obtain the transform formula for this formula, which conjuncts every newly added constraints into this prerequisite. It's here. Yeah. And then we solve the unknown coefficients. Since we have removed all non-polynomial terms, we can solve this first theory of reals. But the complexity is very high because we already have the extension quantification over the coefficient of variables, and there is another universally quantified logical operator. So the complexity is quite high. And we solve this through Handelman theorem. We solve it as a sound theorem over polyhedra. And we solve this through linear programming. So let's take an example. So suppose we have this previously obtained logical formula. So we copy this here, and then we establish new fresh variables, which stands for non-negative real numbers, and then we just write things like this. Here, those multiplicants are just monomials from either n-2 or from this 5. And we need to control the degree of those monomials so as to make the summation finite. And then by a simple coefficient matching, between these two polynomials, we obtain a set of linear constraints for those coefficients and also the lambdas, and we can solve this through linear programming, and then we have the final result, which that we have the 0 here and 2 over log 2 and 2 here. So by our theorem, we can assert that the worst case behavior of this binary search program is bounded by this function. So the asymptotic behavior of this program is log n. So we have performed experiments on some other classical recursive algorithms. We have for merge sort, for closed pair, and for Karatubas algorithm for say polynomial multiplication, and also Storson's algorithm for matrix multiplication. And we also we obtain a quite tight asymptotic bounds for those classical recursive programs. So in conclusion, we first somewhat extend ranking functions technically to recursion, and we show soundness and completeness, and also we do worst-case analysis of recursive programs through synthesis of non-polynomial functions, ranking functions, and we do this through abstraction of non-polynomial terms, and also through Handelman theorem and linear programming. So in the future, we would like to explore our framework to more examples, and we also will make a complete tool implementation. Thanks for attention.
We have time for questions. Yep.
So when you reduce your problem to a linear programming problem by introducing the lambda 1, lambda 2, the multipliers.
Okay.
I thought you would get a non-linear problem because is that because the C1, C2, C3 variables are not on the left-hand side of the
because these polynomials are constant.
Oh, the C1, C2, C3 doesn't occur in phi and phi?
So this is a polynomial where these are unknown coefficients, and these are variables, and we have also these are constant polynomials, and these are sort of coefficients, so we can see that we can match the coefficients at both sides to obtain linear equalities.
So my question is, do you never get C1, C2 variables in the formula phi that you have on the left-hand side of the implication?
Pardon?
The variables C1 and C2.
Okay.
Do they never occur in phi? The phi, the formula phi on the
no.
Any other questions? So I just have a quick one. So in your experiments, you need these templates, right?
Yeah.
So how many different templates did you need for your experiments? Was it just 2, one with logarithm, one with exponentials?
We just control the degree of the template, and we put every possible expressions
I see.
up to this degree.
Yeah. Okay, thank you.
Yeah.
Let's thank the speaker again, please.